Going to look at another case of permutations. So case 4, you see. And what this is instead of arranging the objects in a line, we arrange them in a circle. How does this change the problem? Well, the difference comes down to how the first object is placed. That's essentially the only difference. Let's show you what I mean. So if we have a line, let's say here's all the spots the objects can go. Okay? Now, there is a definite starting point and a finishing point to the line. So if I want to place that first object, there are 6 positions I could put it in, and each one of those would create a different arrangement. You see, when I have a circle, there is no definite or starting point, because you can always rotate the circle and get the same arrangement. So what that means is the first object only has one choice, and that's to go in the circle, because it doesn't matter where you put it. See, imagine I put it in the top position. Okay, it's in the top position. But then maybe I put it in the second position. Oh, that's all right. I'm just going to rotate the circle 1 step backwards. It's back in the top position. So it doesn't matter where you put that first object. But then once the first object's there, now all the spots are defined. You say, oh, well, it's 1 spot to the left of that person, or 2 spots to the left of that person, and so on. Now, what does that mean? Okay, first object, there are n possibilities if we're putting it in a line, whereas in a circle, 1 possibility. Second object, n-1 possibilities now in the line, but now there's also n-1 in a circle. And then n-2, and so on until we place that last object. Essentially the same, except for that first object. So that's what I'm saying, it's all down to that first object. The number of arrangements then becomes n factorial, but we're dividing out by the number of ways that first object could be placed. And that first object could be placed in n positions, which becomes n-1 factorial. So we're dividing the n into the n factorial. Let's look at some questions then. A meeting room's got a round table. I suppose it doesn't have to be a round table, it could be a square table. It doesn't really matter, they're just going around the table. 10 chairs. Committee of 10 people, 3 of them are teenagers. How many arrangements are there where all 3 of them sit together? Oh, maybe they're feeling intimidated. Got to be together. Well, first thing we do is, all right, you 3 want to be together. Organise yourselves in the order you want to be. 3 factorial ways of doing that. Now, we're going to place 7 others, plus the teenagers, so 8 objects in total, in a circle. If it was a line, we'd say 8 factorial. It's a circle, so it's 7 factorial. 1 less. There's our answer. We're going to hold elections now for the chairperson and the secretary. What's the probability that they're seated directly opposite each other in this circle? Okay. Well, if there were no restrictions, going to need to know that because it's a probability question. So I want to know total numbers with no restrictions. 10 people in a circle, 9 factorial, 1 less. Chairperson, who's now made themselves more important, they're now called the president. They can sit anywhere in the circle because they're going to be the first person we're going to place in there. There's only 1 spot they can go. But now the secretary has to sit opposite the president. So there's only 1 spot they can go. We now have to seat the rest of them, and there's 8 other people to sit. Yes, they're going in a circle, but we no longer treat it like a circle because all of those positions are now defined. So it becomes 8 factorial. Just like as if we were putting them in a line. And so there's our probability. And it ends up being 1 in 9. But hang on a sec. Once the president sits down, of the 9 seats that are left, there's only 1 that's directly opposite them. So therefore there's a 1 in 9 chance. As I say there, sometimes simple logic can just be quicker than doing all this. Let's look at an HSC one, quite an old one now. 2002 paper. 7 people to be seated around a table. How many are possible? 7 people, but in a circle, 1 less, 6 factorial. Okay, part 2. 2 people, Kevin and Jill, they don't like each other. They refuse to sit next to each other. How many arrangements are now possible? Well, the thing is, it's probably going to be easier to work out how many where they are together and then subtract that. Do the complementary one. Do whichever one's easier. That's going to be easier. So let's assume that they like each other and they want to be together. Well, 2 factorial ways of Kevin and Jill being together. They just work out the order they want to be in. Now we'll go and place everyone else. 6 objects altogether. That's the 5 other people plus Kevin and Jill have decided where they're going to go. 240, we'll use the complementary idea then. Arrangements will be 720 minus the 240. There must be 480 then where they're not together. Last year's one. Group has 5 students and 3 teachers, and it is to be arranged in a circle. How many ways can this be done if no more than 2 students can sit together? This is how I did it. I said, well, I'm going to start with 2 factorial. The 2 factorial, there they are. Place the 3 teachers in a circle. Okay, 2 factorial ways. I'm now going to use this insertion idea. What I've done is I've created 3 spots that the students can now go into. But we have a condition. No more than 2 students can sit together. Therefore, the only possibility is that they break themselves up into 2 groups of 2 and 1 person by themselves. There's only 3 spots for them to go. Only way we could do it. Well, let's put them into their groups. That would be, there's 5 students. We have a group of 2, 2 factorial. A group of 2, 2 factorial. Hang on, what's the other 2 factorial? 2 of those groups are of the same size. So I also divide by another 2 factorial. So I have selected the groups, but the arrangement of the students is important in this one. So remember, in these groups, A and B are like this. That would be different to A and B being like this. So that will create a different arrangement. So I've selected, now we go and arrange those groups. So the 2 factorial, 2 factorial. Finally, I'm now going to place them into those 3 spots. 3 factorial. We end up with 720 as our answer. Now there are other ways of thinking about that problem, but that's how I approached it. So here's a little flow diagram of my thought process when we get to these problems. Perms and coms. Well, is the question without replacement? Remember I said the key is it with replacement, without replacement? If it's without replacement, then we're talking, okay, I can use perms and combinations ideas. So then, are there restrictions? So if it's without restrictions, fine, I'll just go straight into, oh well, is the order important? Is the order unimportant? If there's restrictions, I've got to deal with the restrictions first. Now, combinations, that pretty much finishes us off. We'll go and do the problem. All right, permutations, now we've got the decision. Is it in a line? Is it in a circle? Okay. Well, if it's in a line, then are we going to use all the items, or am I going to use some of them? And then, of course, we had the situation where some of the items are the same. So these were all the different scenarios that we looked at. 14G.